machine learning and deep learning. And then it will be followed by a few examples of some of the works that we have been doing in the recent past. So what is artificial intelligence and machine learning? So if you look at 1978, the definition was that it is the automation of activities that we associate with human thinking, activities such as decision-making, problem-solving, learning. Then in 1985, the definition was given or changed by two other individuals. At that time, it was proposed to say that it is the study of mental faculties through the use of computational models. Then things evolved. Then in 1991, two other researchers proposed to change the definition to the study of how to make computers do things at which at that moment people are better. Then in 93, the definition was again proposed to change to branch of computer science that is concerned with automation of intelligent behavior. Then let's move on to two decades more. In 2023, 1 year ago, the definition that was proposed by Geoffrey Hinton, who actually got the Nobel Prize for his work on artificial intelligence. He proposed that AI is a new form of intelligence, one that poses unique risks and will therefore require unique solutions. Finally, in 2024, Ishua Ben-Geo proposed that we should call it artificial general intelligence, or artificial general intelligence is a type of AI technology that aims to equal or better human intellect. So let's take a look at the relationship between artificial intelligence, machine learning, and deep learning. Sometimes these terms are confusing. So in general, artificial intelligence corresponds to relates to the field of computer science that is devoted to making computers perceive, reason, and act in ways to have, until now, been reserved for human beings. So how about machine learning and deep learning? If you look into the diagram on the right side, basically it gives a pretty good idea with respect to the meaning of artificial intelligence, machine learning, and deep learning. So if you look on the right side, basically AI refers to computer systems that mimics or copies human intelligence, enabling them to solve problems and understand language. Then machine learning is basically a subset of AI, and machine learning corresponds to teaching systems to learn from data, enhancing performance without explicit programming. So data is inherently related to, or training or learning from data is inherently related to machine learning. Then deep learning, basically it employs layered neural networks to find intricate patterns, excelling in tasks like image and speech recognition. So this particular diagram will give you some idea with respect to the intricate relationship between AI, machine learning, and deep learning. So let's take a look at the evolution of artificial intelligence. The initial concept of AI was conceived by Alan Turing in 1950, and then in 1956, that is the first time when the term AI was used. Then in 61, the first industrial robot replaced humans at assembly line. So in other words, that is probably the beginning of the first application of the concept of AI in the form of robot. Then in 64, a chatbot named Eliza was developed at MIT, followed by a general-purpose mobile robot developed at Stanford in 1966. Following that, basically nothing was done for about 2 decades, from 1971 to 1990. In the area of AI, we call it AI winter. Then in 97, IBM developed a computer called Deep Blue. That computer actually defeated Garry Kasparov in a chess competition. Then in 98, an emotional intelligent robot called Kismet was developed. Then in 99, Sony launched a pet robot called Dog, pet robot dog called Eyeball. During 2001 to 2010, a lot of work was done in the area of AI, especially with respect to robots. For example, in 2002, iRobot launched autonomous vacuum cleaner robot in bulk format. Then in 2009, Google built first self-driving car for urban conditions with the use of AI. Then in 2011 to 2010, during that decade again, tremendous work was done in the area of AI. So in 2011, Apple's Siri and IBM Watson was developed, followed by Eugene in 2014, which is a chatbot that passed the Turing test. Amazon launched Alexa, a voice-enabled intelligent virtual assistant. And then in 2017, Google's AlphaGo beat the world's best Go player, KG. Then in 2020, however, things changed dramatically with the introduction of generative pre-trained transformer-based AI, which is called GPT-3. Then in 2022, as all of us know, the chatbot was introduced by OpenAI. In 2023, there are basically major discussion started regarding the regulation involving AI technology. And then the AI technology basically peaked in 2024 with the awarding of Nobel Prize to two researchers for the utilization of AI models, especially for solving fundamental physics-related problems. So what is GPT? GPT stands for Generative Pre-trained Transformer. Basically, it corresponds to a family of AI models that can generate human-like text, and millions of people actually are using GPT. Then ChatGPT, which is a more commonly used term, and most of us are familiar with it. It corresponds to AI chatbot. Basically, they uses natural language processing to come up or to generate human-like text. Model predicts the next word in a sequence based on what is learned from the data. It is also trained using reinforcement learning, which basically implies that it receives feedback from humans to improve its responses. And this was developed by OpenAI. So let's talk a little bit about the problem statement and motivation. Basically, we are interested to utilize the advances in data availability, computational power, and algorithm development. And then this has made AI and machine learning more accessible and applicable across industries. In particular, with the tremendous growth in the computational power, the concept of AI, machine learning, and deep learning became a reality. So AI machine learning basically offers the potential to solve complex problems in multiple domains. For example, healthcare. It is widely used for diagnostics, in finance, especially for fraud detection, and everyday automation, like smart assistant. We use it every moment in our cell phones. For example, if we use Apple iPhone, we are using Siri, and then in Android and other cell phones, we have other types of AI-enabled technologies. So let's talk about some key AI machine learning concepts and techniques. Anytime we talk about AI machine learning, obviously we have to deal with data sets, or we refer to data sets, models, training, features, and levels. So let's talk first about data leveling. What is the meaning of data leveling? So when we say data leveling, basically it corresponds to a data point. In other words, a data point is assigned a specific value or category, which is used to train the machine learning model. And then there are two types of learning. One corresponds to the data, and where the data is leveled, and the other type of learning where the data is not leveled, and we call it unsupervised learning. So, what are the main types of learning that we use in AI, machine learning, and deep learning applications? So, in general, as I said, supervised or unsupervised learning. In supervised learning, basically it uses level data, input and output, while an unsupervised learning does not use labeled data. Then this other category is reinforcement learning, where it trains software to make decisions to achieve optimal results, and basically, excuse me, it is similar to humans' trial and error learning process to achieve their goals. There is also another category that corresponds to semi and self-supervised learning, which basically uses a combination of supervised and unsupervised learning. With respect to the task, in general, we use it for classification, for example, image classification, segmentation, and regression, mainly for object detection, clustering, as well as other applications. If you look at the upper right corner of my slide, so for example, if I look into machine learning, let's say it corresponds to supervised learning, unsupervised learning, and reinforcement learning. Supervised learning uses level data. Unsupervised learning uses unlabeled data. And reinforcement learning, basically it learns from the, it trains the software to make decisions for achieving optimal results. In other words, it corresponds to a reward system. So when you look at classification, if you look at the lower right corner of the slide, you'll see that there is a picture with a dog in it. So when I look into the concept of classification, basically our intention here is to see, can I classify or can we classify as a dog? Then if you look into the detection, which is the middle image in the lower right corner, then I have two pictures or two objects there. One of them is a dog, the other one is a cat. Now the question is, what is there in the image and why? For example, if it is a dog, can we basically detect the object as a dog, and then the other one is a cat, can we classify as a cat? Then when you look at image segmentation, basically that image will basically correspond to a cluster of pixels. For example, all pixels corresponding to the dog will show up as pixels in one category, which is shown in red, and the pixels corresponding to the cat, all of them will show up in this particular case, after image segmentation, will show up as a cluster of yellow pixels. All right, again, I'm still going through some initial concepts, and then we'll go into these actual applications. So anytime you work with AI, machine learning, and deep learning applications, obviously we have to deal with tons of data. So the preparation and pre-processing of data is critical. So these are some of the steps that we have to go through in order to make sure that the data is processed properly. So you start with the initial step of data profiling, then you have to clean the data, then you have to reduce the amount of data by eliminating the redundant information. Then we have to do data transformation. You can do principal component analysis, you can do space domain to frequency domain, and similar type of data transformation. Then you have to do data enrichment followed by data validation. So here is here are some examples of most recent AI and deep learning and machine learning structure. The first one shown in the upper left corner is called AlexNet. This particular architecture involves an 8-layer deep convolutional neural network. It is a pre-trained network, and if you train this network using a data set, let's say ImageNet, it can classify images into, for example, about 1,000 object categories. If you look at the upper right corner, this one is called GoogleNet. Excuse me. And the GoogleNet is a 22-layer deep learning neural network. It is also a pre-trained network. And if you train this network with ImageNet data set, for example, this one can also classify various types of images into at least 1,000 object categories. If you look at the lower left corner of the slide, this particular example corresponds to something called ResNet. This is also a convolutional neural network architecture that avoids a problem which is called vanishing gradient problem. Normally we encounter that in other types of architectures, and it allows to construct neural network with up to thousands of convolutional layers. The middle one that you see in the lower middle portion of the slide, it's called UNet. The name UNet comes from the picture. It comes in the form of a U. It is also a convolutional deep learning network used for image segmentation. In general, it has 4 blocks on the encoder side, which is the left side of the architecture, and 4 layers on the decoder side, which corresponds to the right side of the architecture, and those encoder and decoder sides are connected by a bridge. Finally, on the lower right corner, we use something which is called vision transformer, which is a rather recent concept. And vision actually comes from the word computer vision. It's not our vision that we use in the traditional sense. It is also a model used for image classification. All right, so in today's talk, we'll show you some example corresponding to UNet and vision transformer. So here is a more detailed diagram corresponding to UNet. So on the upper right corner, on the upper left corner, you see an input image, which is a 572 by 572 image. It goes through various transformations like 3x3 convolutional layer. Then it will go through a rectified linear unit. Then it will go through some other steps, which is called copy and crop, max pull, up convolution, and then followed by other convolutional layers. So in a nutshell, basically it is a convolutional deep learning neural network used for image segmentation. It includes 4 encoder blocks on this side, and then 4 decoder blocks on the other side, on the right side, and it is connected by a bridge, which is known as this. The encoder path or segment is also known as contracting path. Basically what it does is it will reduce the spatial dimension by 50%. For example, here you have an image. After it goes through the conversion steps that I mentioned in here to 568 by 568, and then it will reduce the size of the spatial image by 50% as we go through it. So it becomes from 568 by 568 to 284 by 284, and then from here it will go from 280 by 280 to 140 by 140, and then it will go down from 136 by 136 to 64 by 64. On this side, the size of the images will be reduced by 50% as we go through the steps, and then it will double the number of filters. Okay. For example, here you have 64 filters, it becomes 128, 256, 512, and then it will go through the bridge. When you come to this side, actually the opposite steps will happen. The size of the images will increase and the number of filters will go down, and finally you will get the segmented image, which is shown in here.
Professor Alam, may I request you to complete your presentation within next 3 minutes? Right. 3 minutes.
Thank you, Professor Hussain, for mitigating the background noise. Yeah. So this one is an architecture for vision transformer. It is an alternative to convolutional neural network based techniques for computer vision applications. It is slightly less data efficient, but it has higher capacity when compared to convolutional neural networks. It basically decomposes an input image into a series of patches, serializes each patch into a vector, and then it maps it to a smaller dimension with a smaller matrix multiplication step. Vector embeddings are then processed by a transformer encoder as if they are taken as embedded. And I won't go through all these steps that you see here. Basically, this particular segment shows how the vision transformer works. And then this particular diagram that you see on the right side corresponds to the transformer encoder. You can look at some of our publications to go through to get a better idea about all of the concepts. And there are tons of publications on each of these techniques. So in order to implement AI, artificial intelligence, machine learning, and deep learning concepts, there are many tools that are available in the market. Some of them are in the open domain, some of them you have to buy. Examples include Julia, Google Cloud, AWS. This one is developed by Amazon, Julia, TensorFlow, PyTorch, Keras, and similar techniques. So nowadays there are a lot of tools that are available that are not available perhaps even 10, 15 years ago. Now let's talk about some fundamental definitions with respect to the evaluation and matrices that relates to the evaluation of and assessment of AI, machine learning, and deep learning algorithms. So if you use regression, then we use some matrices. For example, MSP corresponds to mean squared prediction error. Then MSA, which corresponds to minimum sum of absolute error. Then R square is also a metric that measures how well a model fits the data. Then for unsupervised models, we use something called rand index mutual information. For classification, we use precision recall, ROC curve, region under the curve, and then AUC, area under the curve, and other parameters that or matrices that are used corresponds to CV error heuristic methods to find K. Then BLEU score, DICE score, and things like that. For example, CV error assesses the accuracy and effectiveness of a computer vision model. So if you look on the upper right corner, then there are some relevant elements with respect to the false negatives. And then the right side corresponds to the true negatives. If you look into the true negatives area, you will see there is a red segment. So if your algorithm recognizes something as false positive, then those detections are shown as in the area of are shown as red. Similarly, if you are looking into the false negative area and it comes as true positives, those are shown as green. So what is the meaning of green and red? Basically, it corresponds to how many retrieved elements are relevant. That corresponds to the precision area, which is the bar in the middle. And then how many relevant elements are retrieved. If you look into the recall, then recall will correspond to the number of true positives divided by the area that you see in the denominator. Similarly, with respect to the ROC curve and AUC, basically we plot a curve like this, which is a plot of true positive rate with respect to the false positive rate. And then the idea here is to look at the curve and see what is the trend. So the better, if the curve moves into the upper right corner, for example, corresponding to this one, it means that the algorithm is the best. And if you hit here, which is basically 100% true positive rate and it has 0 false positive rate, it means that this is a perfect classifier. So here are some definitions, and I'll go through this slide rather quickly. Accuracy, precision, recall, F1 score, best coefficient, intersection of variance, and we choose appropriate metrics for a particular algorithm.
DICE coefficient বলেন নাই
will play a critical role with respect to identifying the function of the given algorithm.
Professor Alam.
So here is an example that I wanted to go through. This is one of the paper that we published about 3 years ago. This one corresponds to the detection of eye disease. So the picture that you see here, this is a picture of a regular eye. Our objective here is to figure out, is to segment this the series of images and then using UNet. So these are the four important steps that we mentioned. If you look at this particular block, then we observe that it corresponds to all the layers, all the steps that you see on the left side. And this is the bridge that we mentioned between the encoder and the decoder block. And on the right side, these are the decoder blocks, and this is the output image that you see. So the output image that you see here corresponds to this particular one. This is the segmented image. So when an ophthalmologist looks into the picture, then the ophthalmologist can figure out very quickly whether there is any issues with respect to the nerves in the eye. Nowadays, AI technology is very widely used for medical diagnostics. In this case, we are looking at the detection of eye diseases using UNet-based AI algorithm.
Professor
So if we compare our algorithm with respect to alternate algorithms, here are some results that you can see. On the upper row, you see the test image, and then
Professor Allo, now requesting for conclusion. One more slide. Please do the conclusion.
Okay, I'm almost done actually. I thought I had about 30 minutes. Okay, that's fine. So in here, basically it shows that the algorithm performs very well. Let me, I'll not go through the ROC curve for the sake of time. This is the performance of the algorithm with another data set. Again, the algorithm works very good with respect to that. Another application is crowd counting, because in Bangladesh in particular, we have hundreds of thousands of people in meetings, and security problems occur, conflicts occur. So for those kind of scenarios, actually, we can use our algorithm to estimate the number of people. So for example, this is the ground truth. Here it says 218 people. The algorithm predicts that it is 219. If you look at here, it is 412. Here, the actual detection is 423, very close to the estimated technique. We also have a technique where you can detect or estimate the number of people in a crowded area using mobile techniques. Here is the architecture, and I'll go to the, this is the detailed architecture, and here is the result. So for example, in this case, there is a procession going on with about 1,557 people, and our algorithm estimates that it's about 1,543. The beauty of this algorithm is that you can actually use this algorithm in a mobile device. This is a final example that I wanted to give. You know, elderly people, when they fell, they break their spinal bones and things like that. And then doctors actually repair it by actually putting screws on the back and connecting them together. So here is something that is installed on the back of a person. This is actual image. And the idea here, after 10, 15 years, it doesn't work as good. So can we actually retrieve these images from the physician's office and enhance the quality? So if you use a vision transformer based technique that we used, basically this is the quality of the image. And these are images that are developed using other techniques. This is using vision transformer. And you can see the difference between this image and that image, and physician can look at it and then figure out what needs to be done without actually any physical intervention on the patient. This one is called makeup transfer from one person to another person. This is actually very useful for detecting fake images. And again, this particular example shows, this is the reference image, this row, this is your source image, and you can see we are transferring the lipstick from this image to that image, from this image to those images, from this image to those images. And here is another example with respect to alternate techniques. These are the examples using other existing techniques, and this is the output that you get using the technique that we developed. Now this may sound very trivial, but in reality it plays a huge role with respect to detecting fake images. There are a lot of issues with respect to the ethical and legal implications of AI. I will basically throw this slide without going through the details. Future trends, growth of generative models.
Now we have to stop. Now we have to stop. I mean, we are
sure,
really out of
so
time.
this is my last slide. So key points are transforming industries by solving complex problems, and then challenges and ethical considerations, and future outlook and open question. AI ML advancements include generative models, quantum computing, personalized medicine, and how can we harness AI responsibility for greater good while mitigating risk. That concludes my presentation. So if you have any questions, I'll